Hello and welcome to this webinar, Transforming Lab Automation for Cellular Applications. I'm Lee Rahman, Publishing Director at DDW. Today's webinar will be presented by Russ Green, Product Lead at Automata Technologies. Automation has long been a buzzword associated with leading science, yet even in the most advanced labs, it's usually only applied to specific assays and methods. However, by building automation across your full lab workflows and integrating it into existing protocols, Biotech R&D can be transformed. In this talk, Russ Green will discuss the key pillars of automation across lab environments to increase throughput, enhance data governance, and improve result comparability. Russ Green looks after product strategy at the synthetic biology and drug development disciplines at Automata. He started his career as an academic studying molecular structures using crystallography, then holding strategic roles at numerous life science technology businesses, including Beckman Coulter. Green guides product development to best meet the automation needs of the life science industry. I'll hand over to you now, Russ, for the presentation.
Hi, and thanks for joining this webinar today about transforming lab automation for cellular applications. I'm actually going to not start off speaking about cellular applications. I'm going to speak about automation a little bit more generally, and I'm going to make some statements about the automation world that we live in right now in life sciences. And I'm also going to say some things that might be obvious to many, but maybe not to all, about how you transition from your current state to thinking about that automation journey. And then finally, I'll come on to talk about how this all is summed up in cell culture applications. One thing I want to say at the very beginning is that we have to make an assumption that the future lab state is an automated one. And to what degree that might be automated is up for some discussion. But I would say that adoption of automation in life sciences right now is perhaps not as great as we might think it should be. There are some really excellent pockets of adopted automation in certain parts of our industry, and then there are many parts of our industry that are completely unautomated. And I think if we want to move towards a state of generating more data of high quality in a fully digitalized space so that we can start thinking about utilizing bleeding edge technologies such as AI and ML, then we need to move away from thinking about things as purely manual operations and start freeing up people to be looking at some of those new technologies. And we can only do that through automation. So I think if we make that assumption, we can start asking the question, why are we not more automated than we currently are? And we have tried over the past several decades to address automation in life sciences, and there are some really excellent solutions out there. It may well be that right now, one of the challenges we have is we either think about automation as being small, discrete boxes, which are really good at serving a particular task, but perhaps aren't very adaptable to something more robust. Or it may be that our experience of automation in the industry has been about some large monolithic system built to do an excellent job of delivery of a very high throughput or very complex workflow, but has been very hard to adapt something different. And also perhaps has been hard to adapt for the company that has it when people have moved on or when new people have come in and wanted to be trained up on that platform. And these are some of the specific challenges I don't think we've addressed particularly well in our industry right now, ones of scalability and usability and adaptability. And so people have got a slightly jaded view of automation outside of those experts that are great evangelists and enthusiasts for those solutions. So at Automata, we like to think about automation as being open and integrated. This is the only way we're going to try and address some of these problems, is by really thinking about what those words actually mean. And as part of that, and I'm going to come back to this in more detail in a moment, we really are trying to think about automation from a capability-centered world. And that will become clearer what I mean by that when I get into the second half of this content today. But when we think about open means a couple of different things. So open may well mean just being supplier agnostic. I have a very particular view about this, that the lab of the future for me is not going to be provided by any one supplier. It's an ecosystem of players, both physical suppliers and digital suppliers, so device suppliers and data handlers. And with that, we as an integrator of systems, as an automation provider, need to be able to work with all of those different suppliers, thinking about how we bring together both devices that are best in class at doing what they do, and digital solutions and how we integrate with that data and how we provide that layer of interoperability through the lab. Another aspect of open, which perhaps relates back to something I was saying before about how we can adopt automation at a greater scale, is thinking about how we create spaces that are more inviting for humans and robots to work together. There are some really simple reasons why this might be useful. One of them is that some of the devices we like to integrate onto these systems are really expensive, and we want to maximize utilization on them. And if we're purely tying them up into an integrated system, then we're no longer able to use them effectively from a manual perspective and maximize the usage. And there have been some really good solutions for this in the market, thinking about how we take some of those current designs of systems, which are typically inward facing towards a robot, and how we then might add on docking carts or rotating platforms or kind of solving this particular problem through technology. The challenge I have with those systems is that you then need to effectively reconfigure your system every time you want to have a human interacting with some of that device space. In the automata space, we're really thinking about how we create automated systems that are the inverse of that classical design, exposing the frontage of those devices to both humans and robots at the same time. So if we think about what we're doing at Automata, and this is, I'm not going to speak very much about Automata's products today, but what we're trying to do is re-engineer the lab bench and build automation around that space, partly because that's the kind of lab furniture that we're used to right now, and it fits into the existing spaces as we migrate from an unautomated state to an automated state. But also, if we think about these lab benches as modules of automation, the modularity of those allows us to scale so easily in a couple of different levels. If we want to scale in capability, all we need to do is add on an additional bench or benches to add on an additional device to deliver that capability. And if we want to scale throughput, we can look at the system holistically and understand where the bottlenecks are. And rather than having to build out complicated extension platforms or even duplicating the entire system, we can just add on the capabilities required to unbottleneck a throughput increase. So in either case, we're just talking about adding in small numbers of benches to both to expand and scale our capabilities and throughput. So now I want to talk about what I call journeys to automation. So I want to think about how we go from perhaps a completely unautomated state into one of automation adoption. And this is the piece where, if you are an automation specialist, a lot of this should be fairly second nature to you, but I would debate whether we always go on this journey in a correct way and really understand the root cause of the problems that we're trying to solve and the goals we're trying to get to before starting to implement automation. So how do we begin that journey? Well, at the very start, we really need to think about what our goals of automation might be. And there are often preconceptions about automation being just faster, for example, and actually often it isn't, it can be, or maybe automation delivering on reproducibility. These are all potential goals, but we have to identify which one or which several of those are critical to our success as we migrate towards automation. And that could be achieving a greater throughput. It may well be, yes, I want to run this particular workflow at a much higher throughput to generate much more data. It might be quite simply that I want to reduce my number of manual interactions. I'm seeing maybe a large number of errors, or I want to free up people to be doing other things right now as compared to running a fairly mundane task. And so I want to implement automation, not to do things faster, but just to decrease the number of time my human operators are spending interacting with those devices. And it may well be that it's a pure like that sort of big goal of generating more data of higher quality, which kind of wraps up both throughput and reproducibility into one. And it could be one of these goals, it could be several of these goals, it could be something completely different. But if we don't identify that, it becomes very hard for us later on to think about how we optimize the design of that system to achieve those goals. One mistake that's often made, and I'm not going to exclude ourselves from this particular part of the conversation, is that we often start thinking about building automated solutions from the devices we have or from the solutions that we sell. And that's fine in some ways. That may well be what we need to do. We may well have high valued pieces of equipment that we have to build around. But given the freedom and choice, we should really be thinking about what capabilities we need to drive that workflow towards the goals that we have. And if we start thinking about that purely from I have this robot, or I have this transporter, or I have this large liquid handler, or something of that type, and we start and build a system around it, we're already biasing the solution that we might have and potentially not ending at the most valuable solution for that problem. So what do we do after defining a goal? Well, I would say we need to think about what the scientific operations are. This shouldn't be too complex for anyone. So here I have a fictitious workflow. It's a little bit of a nonsense, but it just represents perhaps some kind of assay that we wanted to automate. And in the real world, if you're really looking at the scientific operations, you'll be going to a far greater depth of granularity. For example, how much volume do I need to move and at what accuracy? But here I've just got a representation of a process where I'm going to take some chilled samples. I'm going to have to aliquot those and dilute them. I need to seal that plate prior to incubating them. Then I need to wash away the liquid that's in those plates and replace it with another one, dispensing some further reagents, shake those plates, and then image them. And finally, steps that are often neglected when we think about the details of these processes is some of the more menial tasks, such as disposing of labware or disposing of reagents. And so I'm going to include that in here as we go through the process. So having considered all my scientific operations, I now want to think about what is the best in class way to achieve each of those operations, given the parameters within them and the goals that we're trying to achieve. Now, in this particular example, perhaps I'm not looking to do something particularly high throughput. I just want it to be walk away. So in my chill step, I've got the representation of an incubator here. It's not particularly high capacity, but it's the best device out there for achieving the kind of environmental conditions necessary for storing my samples and delivering it in an automated way. For my aliquoting step, I need to do something reasonably complex in my pipetting in this case. So I want to have a liquid handler, which can do something more flexible than perhaps just a straight transfer of liquids. But when I come to doing my dilution, having handled the more complex liquid handling, I can now just use a dispenser, just do a blanket dilution across that plane. It doesn't need to be anything particularly complex. Now, my fourth step here, I get on something which isn't necessarily a very exciting topic of conversation, but it often represents the crux of some of the conversations we have as we move from a manual state to an automated one. So the scientific operation I had represented here is seal. And yet the image I've chosen to represent that as the best in class to achieve that is actually a lidded plate. Now, if we wanted to consider sealing in an automated environment, and perhaps we have to, perhaps our workflow absolutely demands a plate seal, we need to actually put on some reasonably heavy devices into that platform. So we have to put in a sealer and a peeler to remove that seal from the plate if we wanted to carry out any more liquid handling. That layers in both an additional couple of devices, which, if I'm honest, could potentially also be failure points. The more devices we put into a system, the more complex it becomes and the more possible points of failure we have. But also it adds an awful lot of cost onto that system. So in this particular example, we chose to have a look at the scientific validation of this process and realize that actually we didn't need to seal them. A lid was perfectly acceptable. And now, rather than have to layer on additional devices, all I need to do is consider that extra piece of labware on the process. Having made that decision, we can then incubate those plates. And then I come on to this wash step. And this is another area I just wanted to focus on very briefly in this process, where washing is actually, you could break that down into a subset of operations. So plate washing is a series of iterative aspirate and dispense steps and could be done by a liquid handler. But there are fantastic devices out there that run those operations in a very high throughput way. So why would I not just use one of those ones as the best in class way to achieve that capability? So then moving through the process, I'm using some other devices here. And the last step I really wanted to talk about before throwing things away is, in this step, it's the imaging. Often one of the fixed points in a workflow, apart from certain aspects of the sample preparation, is the way that we do the detection. And there's often a device already available, and quite often it is already automation friendly that we might utilize in that workflow. And so this imaging device may well be, in this case, the one that's already exists in the lab. Then last but not least, throwing things away, best in class device for doing that, probably a trash can. But if we don't consider where we can put that on the system, we're going to have some real problems when we come to actually validating this process later on. So having considered all the capabilities we've got, we then need to stitch it all together. And this is also where working hand in hand with the expertise of an automation provider can really drive this process to something successful. So something like the Automata platform allows you to design these work cells and then iterate upon that design and test them in silico, which means that we can start figuring out where the bottlenecks are in the process. Maybe I need to add in an extra dispenser, but in this case, I'm really looking at just the transporters, and so I'm adding in these robots through the process. And perhaps as I go through that, I discover that actually I have some real bottlenecks in the back end of this process, and so I need to add in some more transporters. The other aspect of this that I don't really touch on as we think about designing these systems, iterating on these designs, is the data side of that process. Every single one of these devices and the workflow as a whole is generating data that we need to consider as in the form of operations. And so as we're thinking about this, we need to consider how we track that data all the way through this process and ultimately tie it from the sample that enters the platform into that crucial imaging data that's generated as part of this workflow. So in summary, we should really be designing automated systems based around our goals and a series of capabilities that are absolutely best in class for those processes. And if we do that, we may discover that on our journey to automation, we just want to start off with something simple and scale upon it from there. So this example here is just something very simple for doing some molecular biology workflows, and it may well be that that was absolutely right for achieving the goals that we set out to when we wanted to embark on automation. And because it's small and easy to use, it's going to make it easier to drive adoption in our laboratory as well. And then we can think about how we start scaling up to something more extensive. So then how do we start thinking about some of these examples? So here I have an example of how we had a particular goal of driving a particular workflow down to a low number of manual touch points. So we could have chosen to optimize this particular assay, which in this case, it doesn't really matter exactly what it is. In this case, it was a ligand binding assay, so an ELISA, where we had an objective to reduce the number of manual interventions so we can maximize on staff usage for other activities in the laboratory. And so our approach to building out the system design here was to maximize this system both in terms of capability, so we could run all the tasks that we wanted it to, and capacity, so we could hold all the piece of labware for running a particular batch. And actually speed itself, whilst as long as we did it within a certain time frame, was not really the target. Now the outcome for this was this enormous reduction in manual interventions for this platform, which was great. That's what we set out to do. Now they didn't reduce to zero, that would be unrealistic because you still need to load and empty these platforms. And you also need to factor in a certain number of errors that may occur over the lifetime of that platform, which could also generate manual interventions. But what we've done here is that by designing that platform in a particular way, we could reduce the number of manual interventions down to something almost insignificant. As another example, one that's more common perhaps to many people's thinking is how do we achieve throughput goals? And this is a great example that we've been through recently where we were targeted with achieving a throughput of less than 2 hours for a batch of cells. And I'm not going to go into the details of what this particular process was, but suffice to say that the automation options that were being explored before we entered this conversation were quite some margin away from achieving that kind of throughput. And so what we did with the customer working hand in hand is we drilled right down to where the bottlenecks were in this process. And the bottlenecks here were caused by the fact that they were considering automating this. It's quite a liquid handling intensive workflow. So there was an assumption made that a large liquid handler was going to be the best way to solve this process, and which I think is quite a reasonable assumption. It may well have been the case, but actually when we looked into the process, we discovered that within all of those liquid handling steps were several discrete units of operation that we could break down. So if we then broke up all those liquid handling operations into individual systems, we could then utilize some best-in-class tooling for that liquid handling to then achieve a much higher throughput and achieve a far greater level of parallelization. And so the outcome of this was we were able to automate this process in around about 90 minutes, which was an order of magnitude around about 8-fold versus the existing automation platforms they were looking at. So coming back round to the title of this particular talk is in terms of migrating automation of cellular applications or bringing automation to cellular applications. How does this apply? And everything I've spoken about, well, everything I've spoken about so far does apply. It's the same thing. So when we think about cellular applications, we need to think about what we're trying to achieve and consider the best-in-class way of achieving that. And I would say that in the cellular world, in particular around cell culture operations and things that are maybe pre-bioreactor scale, so flask or labware-centric cell culture, I wouldn't say automation of adoption is particularly high. And so I'm going to explore a little bit about why that might be, first of all. So why would we want to automate some of these applications if we haven't explored them already? There are a few good reasons why, apart from all of the other ones we mentioned today so far. So a few things that are specific to cell culture. Some of the tasks, such as things like media exchanges, are very mundane and very onerous and can certainly scale up to a throughput that is really, really hard work for human operators to try and achieve. So that's one reason why we might want to do things. Also, building reproducibility in cell culture is also really challenging, and automation can help with that. And then finally, in terms of the things I'm thinking about today, is that biology doesn't stop growing at the weekend. One of the main reasons we get asked about automating cell culture processes beyond the ones I mentioned is that in an ideal world, things like media exchanges or perhaps even something like slightly more complex operations might ideally happen after the end of the working day or at the weekend. And actually what we do right now as we think about these typically is we tend to run or design experiments that don't maximize on the biology, but maximize on the human operator hours, which isn't necessarily going to get the best out of that biology. So why aren't people doing this extensively right now? And again, there are cell culture automation platforms out there right now, and we're also providing them. I just think adoption is fairly low. And some of the reasons why fall into a few different buckets. One of those is that replicating some of the manual manipulations that we do with cells is quite challenging. If we were to consider a cell culture flask, that is a piece of labware which is quite difficult for automation to work with. And then on top of that, if you were to envisage someone working in a cell culture hood with one of those flasks, they're tilting that piece of labware to aspirate the liquid from it. And on top of that, they're tilting the pipetta that enters that labware at a very awkward angle. These are steps that could be recreated by automation, but would be really hard to do so and probably quite expensive and not very reproducible as a result. One of the other areas that can be really hard to think about when you migrate to cell culture is making some of those decisions that we might need to do based on data. So a great example of that, and the most common one, is when do I choose to perhaps split or expand cells? And that is normally based on a growth metric. And you might be measuring that based on a microscope right now. So you need to think about how, as a user, can I port that process into an automated way? And it absolutely can be done. Some of the other considerations that can be challenging, and perhaps more solvable now than they were before, are in the areas of media handling and sterility. So in terms of media handling, again, thinking back to how we do things manually in the lab right now, when you come to doing something simple like a media exchange, you may well have some media pre-prepared in a fridge. But what you'll do is you'll take that media to your cell culture hood and then leave it there for a period of time for it to come up to room temperature. So when you carry out your media exchange, you're not going to be shocking your cells. And we could do that in exactly the same way on an automated system, but if we do want to run it out of hours, perhaps we need to think about how we handle that delivery of chilled media to the platform of an automated system and bring it up in temperature just in time for usage for a media exchange process. On the sterility front, automated systems possibly have slightly different considerations to what we have manually. So clearly we need to have some form of clean air or containment around these platforms. But one thing I would put to the audience here is that typically we use a class 2 hood in a manual environment as our standard cell culture hood. And that may be a requirement, but perhaps when you move to an automated system, maybe it isn't. Class 2 environments typically give us protection not just to our cells, our product, but they also give protection to our users as well. And if we're working in an automated environment, then perhaps we don't need to consider that latter aspect, and all we need to do is provide a clean air environment to protect our cells. So how do we start considering migration from a manual operation to an automated one for cell culture processes? So there are a few things here that just represent a few of those problem spaces I just described. Now, on the rightmost side, you see a 6-well plate. And this is just meant to represent that we need to think about probably transitioning from cell culture flasks for adherent cells to something more amenable to automation. Now, this might have some restrictions in terms of the amount of volume we can now work with, but of course, the other flip side of automation is we could work with a greater number of pieces of labware as well to mitigate for that. But some of these things have to be considered. In conjunction with that, so second most on the right is a picture of an automated incubator. And these are typically designed to work with the same kinds of technology you would utilize for your own manually accessed incubators to create that cell culture growth environment, but now have automation to deal with the kinds of labware represented on the rightmost side of this in terms of both incubating those and delivering them to external to the incubator for collection by a robotic transporter. Moving further from right to left, you can now see one of those very same 6-well plates being tilted in its position. So one of the hardest areas is recreating some of those manual manipulations. And if we think about the labware being part of the solution to that problem, then we can think about solving some of the other parts of that problem space through other forms of robotic manipulation. So the reason why we would tilt this piece of labware is to move all the liquid in a very large surface area, flat bottom plate, into one corner so we can aspirate away all of the liquid. And that gives us an opportunity to represent some of those manual manipulations that might be challenging. And there are other things we might do in this space with robotics to be able to solve that problem. And then finally, on the leftmost side here, we have an automated imager. So this might be one of the other migrations we have to consider, is moving from perhaps measurements made using manual microscopes or manual cell counters to something that is automation friendly, that can take a microplate that is growing cells and make some of those measurements automatically. I've mostly focused on adherent cells so far today. I also want to touch on some of the needs of suspension cells, although I'm not going to go too deeply on this today. But suspension cells clearly have different needs, and actually in the automation world, we've been quite restricted in our options and how we work with these up until quite recently. So there have been shaking incubators available, but they don't, until very recently, represent the kind of environmental conditions that you would get in something represented in the middle here as a large flatbed shaking incubator. And there have been advances, say very recently in the market, in both providing larger throw automated plate-based incubators and also automating the kind of incubator that we see here, allowing us to perhaps work with larger cell culture vessels. But speaking of cell culture vessels, we now also need to think about something that we could transport robotically. Perhaps the flasks that we are working with previously on those systems aren't amenable to automation, and we need to think about something different. And then finally on this space, one thing I would mention is that when we start talking about suspension cells in particular, and you may need this for some adherent cell operations, but absolutely if we wanted to wash or resuspend or passage suspension cells, then we need to think about including centrifuges and obviously automated centrifuges into that process, which just adds some extra levels of complexity into those automated systems. So in the final part of this talk today, I want to start thinking about how we might consider some standard units of operation around cell culture. So what do I mean by that? And when you start thinking about most workflows in the laboratory, you can often drill down to a subset of operations that are pretty standardized no matter what you're doing. So if I think about a cell line development workflow, I will typically seed some cells and then go through a process of iterating upon screening those cells as they're growing and characterizing them, and then expanding those in the selected ones into a larger volume, and going through that until I reach a stage where I've gone from perhaps hundreds of clones down to tens of clones, which I would then want to take forward into further screening steps. So at that stage, I might freeze them down or migrate them into something more like a cell line maintenance process. Throughout all of this process, we're doing some simple operations routinely, such as media exchange, or a data-driven expansion, perhaps from a smaller volume of cells into a slightly larger one, for example, a 96-well plate into a 24-well plate or into a 6-well plate. And these can be standardized into simple units of operation. So that gives me something now to leverage in terms of automation. So I can start thinking about small system designs now to deal with some of those small units of operation. So if I start at the smallest stage, I can now consider media exchange. And this might be oversimplified, but it's to demonstrate that perhaps automation in this area doesn't need to be super complex. Now in this system, I have an incubator and I have a liquid handler connected together with a transporter. And on that liquid handler, I do need to have some specializations. I need to have something sufficient to aspirate away reasonably large volumes of media if I'm working with something like 6-well plates. I also need to have something perhaps for precision dispensing. I don't want to squirt media in a vigorous way onto the surface of those plates because I might dislodge those cells. And then, as I've mentioned previously, we might need to accommodate things like tilting positions to help with some of those manipulations or media warming. Things not represented on this figure that I also would need to consider are clean air containment and perhaps for out of hours operation, some kind of fridge for chilling that media with some kind of inline heating system so that when it's being delivered to the platform is up to the right temperature for delivery to cells. So now we have a small system. What happens if I wanted to consider perhaps layering on some data collection or some throughput capabilities? This might enable me to do something more like cell line maintenance or perhaps even an expansion operation. So in this system, it starts off exactly the same, but I've added on one more lab bench with a dispenser, which I might want to utilize to achieve a slightly greater throughput on media delivery whilst using my liquid handling platform for handling the more complex aspiration steps. And I've also, in this case, added on a cell counter. Now that could be an imaging system for measuring growth. It depends on really what your goals are and what you're trying to achieve in terms of what your analytics are. But now I've expanded this system to handle something slightly more in terms of a walk-away end-to-end process. And you could keep on considering growing your platform in this way. If I wanted to achieve an end-to-end cell line development workflow, I might need to consider adding on a cluster of different capabilities and probably also start expanding my storage and my incubator space as well. But for example, I could add on some automated single cell seeding platforms and maybe a device to measure clonality through the process. Most commonly, we also see the requirement for automated imaging systems for measuring growth of those systems, so I can make a decision about perhaps expanding a cell line when it gets to a certain confluency. And in conjunction with that, I'm almost certainly going to want to measure product quality. Especially if I'm doing something like a monoclonal antibody production system, I'm going to want to measure how much antibodies being produced by their cell lines and use that in conjunction with growth to make a decision about which cell lines get carried forwards. So then finally, I'll ask this question is, what can automation enable in these same cell culture labs that we don't consider possible today? What do I mean by that question? Well, right now, we're often restricted by either the throughput we can achieve manually or perhaps with our smaller integrated system, and perhaps with the processes that we validated. But once we start layering in automation and we start gaining more walkaway time, we start freeing up people to think about, well, what kind of other science would I really like to achieve here? And a great example of that, if I go back to the previous slide, is perhaps I am now making decisions in my cell line development process based on growth and product quantity. But perhaps I could make a more detailed decision if I start measuring things about my product quality, or maybe even looking at the cell phenotype in greater depth. Now, these things are things that I might be doing when I get down to a small number of cell lines, when it's achievable for me to do manually, but perhaps I could start doing this sooner in the process and theoretically start actually gathering larger data sets and more complex data sets when I'm still working in the order of hundreds or even thousands of cell lines in this process, and start gathering data sets that I perhaps thought were not achievable before. And so finally, I just want to speak about, in summary, about how we might build these interoperable spaces. So we should be designing systems based on both goals and the absolute best-in-class capability required to achieve scientific operations to achieve those goals. We should also consider starting off perhaps with small units of operation and building out capabilities as we go through time. And that journey to automation should go hand in hand with the expansion of scientific capabilities and broadening our horizons in what we think we might be able to achieve in terms of our scientific workflows. And what we might look to do is start expanding towards truly human-robot interoperable spaces with multiple layers of robotics and high density of devices being accessed by those automated systems. And with that, that concludes my talk today. Thank you very much. If you have any questions, I'll be happy to answer them.
Thank you for that excellent presentation there, Russ. It was really informative, and I appreciate your time to deliver that today. Before we continue to questions, I'd just like to remind everyone that this webinar will be available to access on demand on the DDW website, www.ddw-online.com. Okay, Russ, if you're ready for the questions, we'll start them.
Yeah, I'm absolutely ready.
Okay, so the first one that we have is, can I work with instruments on the bench while the robot is working too, or is it one approach or the other?
Yeah, that's a really good question. So our systems are absolutely designed so that is possible. Part of the reason for taking this system design approach of having all of the devices facing outwards to enable those systems to be human-robot interoperable. Now, of course, if that system is that device is required for an automated workflow, then it's entirely possible you wouldn't be able to access it, and that will be indicated through the digital platform as such. But if that system isn't being utilized, or that device isn't being utilized by the automated platform, then absolutely you can unlock that device for manual usage and walk up and use it whilst the robots are still tending the other devices on the system.
Okay, thank you. The second question is, if I have devices that do some of these things already, can I use them? What does the transition to automating these look like? For example, I have an imaging system in my lab right now.
Yeah, that's a great question. When we're looking to design systems, I think if we went back to earlier on, we're often tied by some of the devices in the lab. It'd be great if we weren't. And systems such as imaging systems, as the one that's been raised here, are often some of the most expensive devices available to us in the lab. Now, the simple question we have to ask ourselves is that device automation friendly? If it is, then absolutely we should be able to take advantage of it, but it often comes down to the device itself. If currently you were using a microscopy system with a camera attached to it with a manual trigger, then perhaps that wouldn't be so amenable to automation. If you're using a fully automated plate-based imaging system for gathering that type of data, then yeah, absolutely that is almost certainly something we can incorporate into an end-to-end workflow.
Okay, thank you, that's great. The next question is, you didn't cover much on data. What happens with all the data generated by any equipment in the system that I need to analyze?
Yeah, I realize this was a fairly hardware-centric discussion today in terms of capabilities and system designs. So, brief note about our platform. Our digital part of our platform, which I didn't really share today, is cloud native. And that means that we do consider the data generated by our platform as part of that workflow analysis. So when we build out the automated platforms, we're as much thinking from day one about what that data workflow might be, as well as that physical workflow. And when we're considering integration of devices, we're also integrating the data generated by those devices. What that means at the end of that process, from our perspective, is that we're able to generate a package of data with both the data generated by the analyzers and any process information that's been gathered by that system, both from our own digital execution and from those devices, for example, log files or error states, or whatever that might be. And we're collating all that data into a single package that can be accessed by some other part of the digital ecosystem. So yeah, data is absolutely critical. I mean, it comes back to this question of why would we automate, and really the core of all automation is to generate more data of higher quality. And so that's absolutely consideration from day one of any kind of workflow development or automata.
Okay, thank you, Russ. So can these systems be used at scale, and is there a limit to how much volume or capacity that they can handle?
So I'd bring this back to the goals question in some sense about what does scale mean. Now, scale actually, as we've gone through conversation with customers, has meant a couple of different things. So scale, most obviously, is increasing capacity, like thinking about scaling up a process to something more industrial. And yes, absolutely, these systems can be used at scale in terms of just adding on raw capability and capacity to increase capacity, increase throughput. Scale might also be, can I run multiple iterations of one end-to-end workflow on several instances of that platform, so several hardware configurations. And that's something we've actually done a fair amount of already. Our heritage is actually more in industrial automation. And so this is absolutely one form of scale that is very much of the core of what our vision is for the automation world. And just to give one slight other variation of that form of scale, is that it may well be that scaling is running the same workflow on the same hardware configuration at multiple sites. And with the kinds of platforms that we develop, and with our digital platform, you can run the same workflow on, for example, both sides of the Atlantic on independent work cells in the same way. So depending on what your definition of scale is, yeah, absolutely, that is right at the core of what Automata is trying to achieve in terms of bringing high levels of automation to the life science industry.
Thanks, that was a great answer there, Russ. You only briefly mentioned working with suspension cells. How hard is it to work with suspension cultures on automated systems?
Yeah, that's an interesting one. There are some aspects of working with suspension cells that are actually easier. You don't have to go through all the trouble of dissociating your adherent cells from the surface they're growing on. And that brings a bunch of challenges about how do I deal with trypsin and dilute or remove that from my cells as I go through a splitting process. Some of the bigger challenges around suspension cells actually come in the form of, number one, they require some extra devices, as in the form of centrifugation, I think I mentioned earlier on, and how do we deal with that? One of the biggest challenges they tend to present is actually one of volume. A lot of the liquid handlers that we have available to us just aren't really geared up for the volumes that we're trying to work with in the automated environment with suspension cells. And some of the incubators that have been available until very recently aren't really designed to grow cells at any scale either. And so people have been addressing this in a bunch of ways, often with semi-automated systems, so we're doing all the liquid handling components and maybe some of the centrifugation steps and things like that, and then putting those into an incubator manually, with some recent advances in incubation technology, both on plate-based and flask-based. Actually, the doors just opened for some slightly more comprehensive end-to-end suspension cell culture workflows. But sort of to summarize, that the problems tend to come from the extra device requirements and from the volumes we're working with, just generating a little bit of extra problems from an automation perspective.
Great, thank you. And the next question that we've received is, can this fit into a non-square layout? And what can I do with my limited space in my lab to implement automation?
Yeah, great question. So coming back to the modularity of the solutions we provide, they're all based on little cubes of lab benches, right? So these can be configured in lots and lots of different ways. Now, when we're tending to show capabilities in these presentations, we tend to show either a linear system or a square system, just because it's easier. Of course, if your lab space requires everything to go around a wall and bend around the corner, then we can accommodate that. If you need a U-shaped system or a T-shaped system, then that's the lab benches are perfectly suitable for this. And one aspect I didn't really mention on this is I did talk a little bit about the robots that tend the devices. This wasn't really a hardware presentation today, but there is a secondary transport layer built into all these benches that sits just underneath where the devices would go and allows us to move any labware in a planar fashion. So that means you could have a big square system or a linear system or a T-shaped system and not be restricted just by the placement of those robots to accommodate that. And this gives us a lot of flexibility in terms of adapting our system build designs to your given lab space. So short answer is yes.
Okay. And we have quite an interesting question here. It's, what do you mean by doing things that we could not otherwise do with our current lab? Could you expand on that, please?
Yeah, I think I covered this to some degree, but maybe it's worth going to in a little bit more depth here. Often when we're brought workflows to automate, we are taking what is being done manually, which by its nature is an inhibited process, either by the throughput of the numbers of people we've got or by the devices we have currently in our laboratory space. And what's been really nice in recent years is we started being able to ask that question with clients. Okay, this actually isn't that complex to automate. What else would you like to do? And we asked a lot of these questions when talking to them. Again, come back to the cell line development question. We looked at what happens a little bit further downstream when you get into process development and say, well, actually, when you get to process development, you start generating a lot more data about those cell lines that are growing. And when we started speaking to a lot of clients about that, they said, well, actually, it would be really useful to start gathering some of that data a little bit earlier. So this is one of the examples I was trying to walk through about perhaps in an automated environment, that starts giving us the opportunity to ask ourselves the question of, if I could wave a magic wand, what would be the data set I'd like to collect here? And that's what I mean by that question. We can start opening up our eyes to some other opportunities of what kinds of data we want to collect and what kind of scientific design of experiment we might actually want to try and achieve here to answer a deeper question than the one we originally posed. So I hope that answers the question. It's a bit of a philosophical question about where automation might enable us to go, not just in terms of scaling, but in terms of deep set capabilities.
Oh, thank you, Russ. That was a great answer. And the final question is, how long does it take to implement an automated solution into my lab like this?
Yeah, we get asked this question quite a lot. There's a really variable answer. So the sort of journey, to use that phrase again, you would go on with Automata is in the space in between having designed and landed on a system and it actually being manufactured and delivered to your lab, we go quite deep into building out what that test program might look like. And building out the system is only one step, right? And that might be, depending on the complexity of the system, small days to significant weeks. The bit that's a little bit harder to gauge is what happens in terms of scientific validation, which again, our team works hand in hand with clients to deliver. It's a very important part of our services business is to go through that system validation with a client. And again, for something well planned and simple, let's just say it is a media exchange, it might be that that actually is as long as that typical cell culture experiment takes to run, so 3 or 4 weeks. Of runtime. It might be for something more complex like an end-to-end cell line development workflow. You want to run through an entire campaign before getting to validation. So system build out, days to weeks. Scientific validation can be significantly longer. It really depends on what we're trying to achieve and what the goals are for that particular automated system.
Okay, thank you, Russ. Thanks for those responses. They were really great. And thanks again for your presentation.
Absolute pleasure.
Thank you. If you'd like to listen to this webinar again, it will be available on demand at www.ddw-online.com. You can now view Drug Discovery World content online on your mobile or tablet or via the new DDW app, which can be downloaded via the App Store or Google Play. Thank you for listening.